speaker for this session is Dr. Frank Dorman. He is the Assistant Professor of Biochemistry and Molecular Biology. He is actively involved with the Forensic Science program on campus too. Before joining PSU, Dr. Dorman worked at the Rastec Corporation for 13 years. His research at PSU is focused on understanding chromatographic separation of trace compounds. His laboratory focuses mainly on techniques of chromatography, especially mass spectrometry. Today, he'll be talking about how his research helps in detecting if water is contaminated. Please welcome Dr. Frank Dorman.
Okay, does the microphone work? There's a surprise. I'm really loud. Put this down lower. Is that better? Yeah. I'll keep you guys awake, if nothing else. Speaking of consciousness, how many of you are conscious of hydraulic fracturing? Really? You guys in the middle? No hands? Never heard of it? Where do you live? The moon? If you didn't put your hand up, I hope it's because you're only semi-conscious and not that you're completely ignorant to the fact that hydraulic fracturing is a huge area of controversy that's been in the news within the last 5 years, but it's not new. It was actually around in the 80s as well. And so was I, unbelievably, still working with it. Take a look at what's current, though. Marcellus Shale gas extraction is a really, really hot area right now, especially right here where we live. Because the Marcellus Shale is a gas-rich substructure that's underneath the earth, about 4 to 5, 6, 7, 8,000 feet down, which means that it's reachable. I don't understand anything about drilling techniques, and I'm not going to go through that, but it does mean that it's reachable in the area where we live. Also, you guys must be conscious of the fact that there's been an incredible wave of increase of drilling over the last maybe 4 or 5 years, and it's economically driven. Property owners are selling massive amounts of mineral rights off to drilling companies, and of course this results in all kinds of political polarization. This is a highly controversial topic. Everyone has a side. Is anybody in this room totally neutral on this subject? How many of you think it's a really bad thing? How many of you think it's a really good thing? Well, you have a couple hands, good. The rest of them will be waiting for you outside. This is a really polarizing issue, but the question is, you have a position on it, but is it a position you took from knowledge? Or is it stuff you read in the newspaper? Because we know what to believe in there, precious little. Right, so what do we really understand as scientists? If I look at this area as a scientist and I say, is there something really to be concerned about here? What's going on? What is hydraulic fracturing? Is it contaminating the environment? Or is it not? Is it a safe practice? Is it something that really allows us to get a huge increase in gas extraction recovery out of these wells, which could be a huge boon to some of these towns in Pennsylvania? This could be a good thing, it could be a bad thing, we don't know. Here's a recent water sample, however, that was collected from somebody's well in Pennsylvania. This was just actually collected just a few days ago. We don't want our drinking water looking like this. Right? And this is the kind of stuff that we see in the news where the press will get a hold of that and say, well, somebody next door just drilled a well and it was fractured, and therefore this is from the we don't know that. You have no idea. It could be totally unrelated. Or it could be related, but it might not be from hydraulic fracturing. It could be all sorts of different things that we can postulate as scientists. And I'm advancing my own slides for some reason. The real question as a scientist is, what is causing this discoloration? And if we can find out what it is it bad? And is it related to the fracking? And if there is a relationship, can we prove it? So one of my areas of interest is environmental forensics, which is a fancy buzzword. It basically says, can you take the science into court and convince the court system that the science gives you accurate data? And therein lies a bit of a problem. Right? First of all, we have to think about how we do this analysis. So we can go to things like DEP websites, which are not all-inclusive. They maybe get us started a little bit, but they're not exactly a huge volume of scientific literature. And we can look in the PA DEP website, which is the Department of Environmental Protection, and we can see that these are the types of compounds that Pennsylvania says might be used. Well, that's not really all that helpful, is it now? Because I don't might be, and it's not an exhaustive list, but I can look at this and I can say, well, certainly there's some things in there that I probably don't want my drinking water. I don't want diesel fuel in my drinking water. Right, so I can look at this list, but that doesn't tell me that they're actually being used. So it's really not that helpful. But I can go through here and I can see, well, we use polyepoxyalkanols, we use a whole bunch of different hydrocarbons, aliphatic acids, esters, etc. A wide variety of compounds could be used. Right? toluene, xylene, things that I certainly don't want in my water systems. But let's take a look at these types of wells. So here's, again, this is off of Range Resources website. The drillers and the fracking companies are actually a little bit proactive in providing information to the public because they don't want the public to be afraid of this. They actually want the public to embrace it, but we'll hold off on that opinion for a bit. If we look at the way these wells are bored, so we go down several thousand feet and then we go into horizontal bore, which I find really impressive, by the way, that they can actually turn the bit horizontally and follow the shale seam through the ground. And we case a fair way down. I can zoom in on this and show that these casing structures are relatively complex, and their job is to protect the groundwaters from anything that goes up or down the well bore. So in theory, this should provide us a hermetic seal against environmental contamination. In theory, sometimes it doesn't work that well. And there have been some accidents that are well documented. There have been spills. There have been field accidents, and occasionally they've drilled into mine shafts, and they can tell when that happens, and they just move over and they drill in some other location. But accidents do happen, and we have to, figure out how we can protect ourselves from those. But so far, there's been very little to no direct evidence that the fracturing process has directly caused an environmental exposure. Typically, it's anecdotal. So we'd like to understand this process and the materials that are used a little bit better so we can make up our minds as rational scientists instead of just responding to what's in the press. Now, the press does have some documentation of cases. Most of the cases that have resulted in environmental exposure were related to lagoon treatment of waters. So after hydraulic fracturing was taking place, the material that came back up out of the well shaft was recovered in lagoons near the well. And what happens when those lagoons are fairly full and you have a rain event is you can get breaching in the lagoon, and then that winds up in groundwaters. And some of these events have been documented, and there's been fines associated with these. That practice really isn't done much anymore, but that practice has actually resulted in a lot of surface contamination, and this is showing surface contamination from radium. So this is actually a radioactive element that's brought up from the well bore and then deposited on the surface as bore tailings. And it's, again, this is New York Times data, so not exactly scientific data, but this traces back to scientific information that shows that if we mishandle the practices in the field, we can result in contamination events. This is radioactive event. This is not actually hydraulic fracturing, but it does point out a very good indication as to where this is taking place in Pennsylvania. And of course, we're right about in here, right? So we're sort of centered in the hot area of all this taking place. Now, the companies are self-reporting, right? If we go to the websites and we take a look at what they're self-reporting, so if I look at Halliburton's website, they list the materials that they're using. And unfortunately, what's listed is not something that I can understand as a chemist. So when I see something like FR66 as a friction reducer, I don't know what FR66 is. And if I search FR66, it comes right back to Halliburton. So it's kind of a cyclical thing that doesn't allow me to figure out what the chemical composition is. Right, I can look at all these water frac or these safe frac or air frac formulations, and I can see what this is. And one of the subjects of discussion is that, well, wait a second, this is mostly water. This is very little of the types of materials that I'd be concerned about, organic additives. For instance, very little of the fluid is actually organic. However, on a typical frac operation, there may be in excess of 1 million gallons that are put down the well bore. So this might result in a few tens of thousands of gallons of actual organic compounds that are actually put into the wellbore system. And only about 50% of that is actually recovered. The rest of it stays underground for a good period of time. So this does represent a rather significant volume of material. Right? But once again, I can look at range and I can see these different mixtures, and I see things again like NE100, FE100. I don't know what that is as a chemist. It's a nonsensical name. It's a trade name. And companies basically say their position on this is that it's proprietary. Each company feels that their own additives give them a competitive advantage against the other companies, and therefore they're able to shelter what actually is the formulation. And of all the materials that are used, of course, a lot of these things have known health effects. So is this information really useful to me? Not really. I can't actually make an educated opinion based upon the types of information that's available. The listed compounds are not a complete tabulation. There's no actual formulations given. Many people get overly worked up about the mention that chemicals are being used. Well, we live in a sea of chemicals and they're not all bad. So just because they're using a chemical doesn't mean that it's a negative thing. So can we investigate this as scientists? What I'm going to show you is what we're doing in the laboratory, and in about 8 minutes and 52 seconds, I'm going to try to cover a lot of complex separation science and mass spectrometry. So for those that left, they're probably now glad. We use a tool that looks like this. It's really expensive and it's kind of a pain to run, but what it does is it gives me information that looks like this. So this is the separation of the different chemical compounds that were in the fracturing fluid that was used in a well that was in Katanning. And what I can see, and I'm not going to go through how this is done, I'm just going to loosely clump these things into either hydrocarbon-like materials, glycols, or esters and alcohols. And I can see that in this case, through this technique, I found actually about 959 compounds that weren't represented in blanks or lab controls. So there's quite a bit of chemical additives that are being used in this, but that doesn't mean that they're necessarily all bad. However, I can profile this material. And I can go in, and this tells me how I'm figuring out what various things are. But I can look at a well that was bored very, very close to that by a sister company using the same type of frac fluid. And I can see that both of these wells result in a different chemical signature. So as an environmental forensics person, this becomes interesting, because if I see a signature now in the Susquehanna River, I might in fact be able to trace that back to a particular point source, which is kind of cool. So as a forensics, this type of an analysis works really well, but it's hard to explain to court how this works. I'm probably barely keeping your attention. So imagine trying to go to a court and testify in front of a jury with an average 8th grade education, what that picture just means and how I can tell him the information from it. Well, it's pretty hard, because the forensics data user is really the legal industry. Lawyers, judges, law enforcement, and that's what jury of our peers means when we're in the courtroom. They're not scientists by and large. They have an average 8th grade education in the United States, which means they haven't had really any chemistry to speak of. So how do you explain something like multidimensional gas chromatography, time of flight mass spectrometry to an 8th grader? You don't, right? If you try, you'll just bore them and they'll tune you out. So what we do instead is we make that technique that much more difficult to explain, which I'll skip over, and we take something that looks like this. Here's diesel fuel, separated the way that I just showed you, and utilizing a technique that we've got in the laboratory, we can actually display it like this. Now, I'm not going to tell you how this is done. If you're interested, you can see me at the break. But I create a much more detailed separation that gives me a much better graphical representation of the chemical compounds that are in this material. And I'm able to display that either as a contour plot or as a surface plot. And you can see my original separation back here. If I take this plane of information and collapse it in this direction and tilt it on edge, I wind up with the original separation. We've just got a really fancy way of deconvolving things by chemical class now, so that I can produce a picture that, again, I can go backwards and I might be able to say that perhaps these are the important molecules or chemical compounds that allow me to differentiate one sample from the next. And by showing the picture, it's much more easily distinguishable by a lay audience. Right? So if we do that on hydraulic fracturing materials, we get these sorts of things. So here's a frac material that came up from a well bore in Connellsville. We can zoom in on this and we can see these sorts of representations. This is hard to read. It's black on blue, which is the opposite of the Kenny Wayne Shepherd song. So if we look at this, we can see that this is actually dominated by saturated hydrocarbons. The overall formulation of this frac material is basically saturated hydrocarbons, medium petroleum distillates. I can zoom in this case, this is back to that Katanning well, and I can see that that's more dominated by polyglycols. The picture immediately is recognizable as different. Right? To even people that aren't schooled in multidimensional chromatography, you can easily distinguish that those two pictures are different. And I can zoom in on there, and clearly I see I'm circling heteroatomic containing hydrocarbons in this case that show up in addition to the saturated hydrocarbons, making the Katanning well different than Connellsville, and therefore it's more easily explainable in court. I can zoom in on a certain area and I can say, well, let me find out what that particular compound is, and I can actually use an even more expensive instrument than the one that I've shown in the previous slide. This one's about $1 million, but it gives me very, very accurate molecular weight information that I can then back calculate what the molecular formula is of the compound that's being identified. So in this case, I know that the peak that's right here has the molecular formula of C13H22. Right, so I can get very specific identification as to what's in there, and perhaps this becomes important in the identification of what came back up out of the Connellsville well bore. And I can use that to trace how it moved through the environment, if it moves through the environment at all. Right, I can compare these two via the picture, which clearly from the audience perspective, you can see that these are different. If I find that same chemical signature somewhere else in the environment, it's very easy now to transmit this across in a courtroom because all they really have to do is look at the picture to understand what they're looking at. Right, now we found some other findings that are kind of cool because one of the things that's commonly done, in fact, driving into work this morning, I was listening on NPR about them talking about wastewater disposal of materials of frac fluids that were taken off for wastewater remediation. Maybe some of you have even heard the same thing. And what we found was, we asked the question, does wastewater treatment actually degrade the types of compounds that are used in hydraulic fracturing? Well, here's a sample taken from well, which is well number 401. I guess we ran out of interesting things to name, so we just named it a sample number. And this was before it went into wastewater treatment. So the truck is sitting in front of wastewater treatment, ready to discharge the contents. And this is what the chemical signature looks like. This is the signature post-treatment. We're able to do this and do some relatively cool manipulations of these where we can take the subtraction of the 401 sample, let's call it that. I can subtract that away from the treated 401 sample and now represent everything moving positive in the Z dimension is something that was not degraded in the wastewater treatment process. Again, there's a lot of high-tech science behind this, but the picture is worth 1,000 words or maybe more. Right, so I can clearly see what's going on here. Specifically, and I can rotate this around so I can look at it in different directions. So here's my original sample, here's the treated sample, here's what was unaffected, and basically what's left behind there are all the oxygen-containing hydrocarbons. So none of those were removed in wastewater treatment, they were discharged into the stream. So now I can track that back potentially to the source of the contamination. Something else is kind of interesting because so far what I've implied to you is that what comes out of these wells is relatively static. And in fact, it's not, which makes my job as an analytical chemist that much more difficult. If I take a look at the well that was bored in Worthington, this is the flowback water that was recovered from the well 5 days after the frac. And it has a certain chemical signature, and it's dominated by glycols and alcohols. So let me resample that same material 11 days later. Same well, everything about it is the same, except I came back 6 days later and resampled, and now the chromatogram is actually dominated by hydrocarbons. So what the well releases back into the bore that's recovered at the surface actually is dynamic. It changes with respect to when I sample. The expectation or the guess as to why is because the material in the well bore is adsorptive to the hydrocarbons and it's not towards the glycols. So the glycols immediately come back up as soon as I discharge them. But the hydrocarbons are actually retained in the well bore longer. So the well's signature changes depending upon when I sample it, which again makes the forensics challenge much more difficult and increases my ability to explain this if I have a better looking picture, if you will, for lack of a better description, than what we normally had. So conclusions, this is work in progress. But this technique, which again, I haven't detailed the technique, I've just showed you some of the output from it. It's much more understandable to the actual user of forensic data. Now, the analytical chemist can understand lots of different types of data, but the court system, my argument is, cannot. Right? The court system is hung up on if the glove doesn't fit, you have to acquit. Right? The court system is hung up on really simplistic explanations. Can you show me a picture that I can just see and say yes or no? Right? Keep all that science stuff to yourself. Right? So as long as the science stuff is valid and can hold up against other expert cross-examination, then I'm okay. Right? I can use it to explain it to a lay jury. One of the things that's clearly obvious is wastewater treatment does not remediate the materials that are used in most frac operations, nor would we expect it to. It doesn't remediate pharmaceuticals and personal care products either, which is why we look at those as well. Wells are dynamic beasts. They change their chemical signature with respect to time. And I think that this technique provides us a really tremendous benefit in being able to explain this topic to the legal community and maybe better understand what's being used. So what was in this sample? Well, we're running it now. We have suspicions. If you want to find out, you can email me. I'll let you know in a week or so when we have the results. But thanks very much for your attention, and questions probably hold you back. Thank you.